So here the question asks us to prove that this space is not a Hilbert space with respect to this inner product. So they are given, they gave us the inner product function, which is a map from this to the underlying scalar field, and they define the inner product as the we take the first function, then multiply the complex conjugate of the second function, then we integrate from A to B, or rather the interval. So they gave us this as an inner product. So we are asked us to prove that this does not form a Hilbert space with respect to this inner product. First of all, what is a Hilbert space? So Hilbert space is a complete inner product space, which means if you completeness of the Hilbert space means if we pick a Cauchy sequence in this space, or rather the Cauchy sequence in this Hilbert space, the limit of that Cauchy sequence is also in this same space, which means it converges to an element in the same space. So complete, the term of complete means that then what is the inner product? Inner product is simply a function which satisfies certain axioms to the underlying scalar field. So along with completeness and the inner product, well-defined inner product on a space, we can form a Hilbert space. So if the space is not Hilbert space, then it should be rather the incomplete with respect to the given norm, or we can find we can find that the inner product defined on the space is not well defined function. But in this question they are given the inner product is well defined, which they gave us in the question. So in this question we are trying to attack the completeness part of the space. So again, what does this completeness mean? Completeness means for all Cauchy sequence in this space, the limit of those Cauchy sequences should be in the same space. In our question, the space is continuous function space or on an interval a to b. So if you pick a sequence of functions in this space, the limit function, the elements of a sequence in this space contains functions. So x1 is a function, x2 is a function. Likewise, the elements of sequence are functions. So the limit also should be a function. Since this is the continuous function space, the limit also should be continuous with respect to this inner product if the space is complete. But the question asks us to prove that this is not a Hilbert space, then it must be, we can find a continuous sequence of continuous functions which does not converge to a continuous function. Indeed, that's what we are gonna do. Okay. Here the elementary property of inner product space is we call this norm as a norm induced by the inner product. It is defined as the square root of the inner product of vector itself. If in our example we take G as also a F, which means F inner product with itself gives us the F multiplied by the complex conjugate of F, then the integration of A to B. So we simply get the square root of integral. The integrand should be the absolute value, the square of absolute value of fx. So that is that. Okay. Now we consider this continuous function space, which is all the continuous functions on 0 to 1 interval along with the norm induced by the inner product. So here we define the function fnx. This index n represent the functions, which means if we where n goes to 1 to infinity and we have infinite amount of functions here. Simply this function is, we define this function to be on 0 to 1 over n interval, it gets 1 minus nx value, otherwise it gets 0 value. So here the graphical interpretation of the function, simply when it's 0, when the x value is 0, we get 1 here. When the x value is 0, we get 1. Then the x value is 1 over n, 1 minus 1 over n. Here 1 over n and n cancels out, we get 1. Then the function value should be 0. So we get straight line passing through 1 and 1 over n, where the interceptions are 1 and 1 over n. Then the rest of the value should be 0, because otherwise the function gets 0. So this is where the continuous this function is continuous. This function is clearly continuous, so it should belong to this space, this norm vector space. So now what we are going to do is, first we have to show that this is a Cauchy sequence. So here we pick any arbitrary epsilon value and consider the n and m in natural numbers. We are, without loss of generality, we take m to be greater than simple n. So simply we are now going to evaluate the norm induced by the inner product, where fn minus fm, norm of this difference should be the square root of, here's the definition. Here's the definition: square root of the absolute value of the difference between fnx and fmx. Then we square it, then we integrate it to 0 to 1 interval. Here the graphical interpretation of two functions. This is fmx and this is fnx. So simply we divide this full integral to 3 separate cases, which is, first integral should be 0 to 1 over n, then 1 over m to 1 over n, then the last integral must be 1 over n to 1. So in this last integral we simply get 0, that's why I put 0 here. Then in the first interval 0 to 1 over n, we get 1 over nx as the function value for fnx. The function value of fmx equal 1 over 1 minus mx. Simply we plug n and m to this first function, the piecewise, it's a piecewise function. Then we simplify this and just integrate this one. Then we ended up getting this kind of answer. Then we can further simplify it and finally get this inequality. Simply I put the inequality here because I put m minus n to the m plus m. Then we get 2m. Then when we square it, we get 4m squared. The m squared and m squared cancels out. Then 4 over 3n. Okay, now we can put epsilon here whenever n is greater than 4 by 3 epsilon squared. Then our good old friend Archimedean property, we choose the natural number which is greater than this, a real number. This is indeed a real number because epsilon is a real number. So by the Archimedean property we can get this inequality. Therefore the all n and m which is greater than this specific natural number, we get fn minus fm less than the norm of fn minus fm less than epsilon value, which is, by the epsilon n definition, this sequence indeed a Cauchy sequence with respect to the norm induced by the given inner product. Okay, now we consider the pointwise limit of the function. What is the pointwise limit? When n tends to infinity, this endpoints goes to the 0. When you plug infinity there, we get 0, which is this 1 over n value get closer to zero when the n tends to infinity, which is this straight line come along with the straight y-axis or the vertical axis, then we get the function value as 1. That is why I put 1 here. So when x is equal to 0, this function value get 1, then the otherwise it's 0. This is also a function, or rather the limit function, but it not certainly clearly this is not continuous, because the otherwise it gets 0 when x is equal to 0, only get 1. So here this is not a continuous function. So what was our goal here? Our goal was to find a sequence of the limit of a continuous sequence of continuous function which converges to the discontinuous function. So clearly this is a discontinuous function, but the sequence of functions are all continuous. So we found a Cauchy sequence in this continuous function space which does not converge to a continuous function. Hence, we conclude the space is not complete because it's a norm vector space clearly, but it's not complete with respect to the norm induced by that given inner product. Thus, therefore, it cannot certainly be a Hilbert space.